good evening. Welcome, everybody. Yes, I am Simon Ritter, Deputy CTO, the understudy to the real CTO, who's a guy called Gil Teme, who knows far more about this kind of stuff than I do. Anyway, what we're going to talk about tonight is Java patterns. Now, we're not going to talk about the pattern class. We're not going to talk about regular expressions and things like that. So please don't feel that this is going to be that kind of talk. I will say that I started doing a webinar on this a little while ago. And I had this slide at the beginning, which actually had like regular expressions in the pattern class and the matcher class. And I had a sort of a thing on the slide that built out to say, you know, oh, we're not going to talk about this today. Unfortunately, a couple of people on my webinar didn't get to the point where they saw we're not going to talk about this. And so they dropped off the webinar before we even got started. So Java patterns, we're going to talk about usage, and we're going to talk some puzzles. I've got some interesting things. I will get you to vote on the answers to these things, and we'll see how that works. Hopefully it'll be quite entertaining, because I've done this a few times now, and I think it's has some interesting things in it. So first thing, pattern matching fundamentals. Pattern matching's been around for a while. In fact, it's been around really since the beginning of compilers and languages and so on. So back to the 1960s. It was used in Haskell. It was used in awk. Anybody used awk? Oh, quite a few people. Okay, bonus point. Anybody can tell me what awk stands for?
The names of the authors.
Very good. Aho, Weinberger, and Kernighan are the three people who wrote awk. Just a useless piece of trivia. Okay, so what do we actually mean by, if I can get my clicker to work. Working. I'll just keep without the clicker. Yeah, so what do we actually mean by a pattern? And the thing is that a pattern consists of two things. The first is a match predicate. And that's essentially something that we're going to evaluate to see, do we match against this particular pattern? And that determines whether our pattern matches a given target. And we're going to see how this works as we go through. So don't worry too much about details. It's just the sort of basic idea. Is we've got a predicate, so like a test that evaluates the true or false. Do we match against this or do we not? And then we've got a set of pattern variables, 0 or more pattern variables, which will be extracted conditionally based on whether we match the pattern. This is essentially what we're talking about. There are a number of different pattern types. So the first of those is a constant pattern. And this is the kind of thing that you would see if you're using a switch expression or a switch statement, where you're doing case 1, case 2, case 3. So that's matching against the pattern, which is a constant 1, 2, 3. There are no pattern variables associated with that because, well, there's no variable, it's a constant. When we get into more interesting things is when we have a type pattern, which is where we're matching on a type. So a class in Java, a type in Java that we want to do something with. Making things even more interesting is the idea of a deconstruction pattern. This is where we match against a particular type, but then we're going to extract some information out of it. We're not just going to reference it through a variable, we're going to extract some information. Then we've got the idea of a var pattern, which is where we're saying we want to use type inference to determine the thing that we're going to map to in terms of that pattern. We also have an any pattern, and that's where we're going to match against something, but we actually don't care what it is, which kind of seems a bit weird. If you want to match against something that you don't care what it is, how useful is that? And you will see how useful that is later on. Right. So before we get into pattern matching, there's a couple of things that we need to talk about in terms of changes that have been made to Java over the last few years, which heavily influence what we're going to talk about in terms of pattern matching. First of those is switch expressions. So if we look at the switch statement, which was introduced in the very beginning of Java, everybody here, I'm sure, has used a switch statement at some point in their career. The problem with the switch statement is it took the syntax directly from the C programming language. And C programming language is one that really is used mostly for system software like compilers and operating systems and things like that. That's what it was designed for. And there are some things about the way that the switch statement works which make it quite error prone. The key one is the fact that you have to put a break statement in your switch block. And if you don't put your break statement in, you drop through into the next set of switches or cases. Okay, let's have a show of hands. Who here has ever forgotten to put a break statement in their switch? Yes, most people have done that at some point in their career. And this leads to the kind of situation where you go, how is that possible? I put this value in and I'm getting this value out, and that cannot possibly happen until you realize you didn't put a break statement in. There's also some other things around the scoping of local variables, not necessarily too intuitive. Now, if we look at the switch statement as it works from the beginning of Java, this is a very common way of using it, which is that we switch on some value and we want to assign something to another value. Here, I'm switching on the day of the week and I want to assign a value to number of letters, okay? And as you can see from the code, we do switch on day, then we have case Monday, case Friday, case Sunday, number of letters equals 6, remember to put the break in. But in this case, excuse my pun, in this particular situation, we also have another potential flaw, another potential error, which is if we forget to assign a number of letters value, which we could do. So as long as we're using an instance field, the compiler will quite happily assign 0 to it, and we don't catch the error at compile time. What they did in JDK 12, so that's going quite a way back now, is introduce the idea of switch expressions. I'm sure most people here have already seen these. But this was the idea where rather than taking a switch statement, which executes a set of instructions but doesn't return a value, we can now execute a set of instructions and return a value that we can assign to a variable. This code does the same as we had on the previous slide, but as you can see, it's a lot more succinct. There's less lines of code. But we don't lose any of the readability. We can still see exactly what's going on there. Now, what we're doing is we say, okay, switch expression returns a value. We can assign that to number of letters, do it once, and we know that we've made the assignment correctly. Then we've got a set of cases as we had before, but the developers spotted this incredible piece of technology that nobody had ever seen before. It's called a comma-separated list. And what they said was, right, let's have each case have multiple things on the same line, rather than having to have separate cases for each one. So now we have case Monday, comma, Friday, comma, Sunday. It does kind of stretch the incredulity to think that it took us 25 years to figure that out. But what we then do is we borrow some of the syntax from the Lambda expressions. We use the arrow operator, and we say that the right-hand side of the arrow operator is going to be the value that we return from the expression, or it's going to be throwing a new exception. That way, the compiler can check that we are returning something of the correct type, we're returning something from each one, or we're throwing an exception. So that means we can catch more errors at compile time rather than waiting until we do runtime. The other thing about switch expressions, which we will come back to, is that they must be complete or exhaustive. Second thing that we need to talk to about before we get into the patterns is algebraic data types in Java. If we look at a simple Java class like this is something that we write a lot in Java. So I want a point, which is going to contain two values, x and y, which are going to be doubles. So I create my class called point. I have two instance fields, make them final and private. I then have a constructor, which I have to pass two values to. I have to do an assignment from the values that are passed into the constructor to the instance fields. And then because they're private, I have to have accessor methods to say return the value of x and return the value of y. Great. 14 lines of code to do a tuple. Now, I always kind of wondered why we never had a tuple class in Java. And I talked to Brian Gertz about this. And I said, why don't we have a tuple class in Java? And he said, well, we could give you a tuple class, but then you'll want a triple and a quadruple, and you'll want more and more of these things. So what they did was they solved the problem with records. So again, I'm sure you've all seen records already. Essentially what we're doing here is we're saying, okay, well, let's introduce a new special form of class. So it's still a class, But this way, we can get the compiler to essentially generate a lot of the code for us. Now we have the keyword record to indicate that's what we've got. We use the same naming system, so point, and then we use the constructor syntax to indicate what we want to store in the record, XX, Y. Everything else is filled in for us. Because it's a special form of class, we have the braces, we're not putting anything in there, so we just leave them as empty. One line of code to replace 14. Because we have a special form of class, we can also make it generic. So we can add a type parameter T, and then we can store things of type T in our record. We can, if we want to, add more functionality. Because it's a special form of class, we can add things like a method to calculate the area of a circle. We can add static fields. We can't add any instance fields that are not declared in the record declaration, but we can have static fields, so we can put the value of pi in there as well. Java is an object-oriented programming language, so it has inheritance built into it. And we can create type hierarchies like this. We have shape, and we have 3 subclasses, triangle, square, and pentagon. That's all good, but the problem we have is that we can't control easily who can inherit from a given class. I've created that simple type hierarchy. I can say, okay, triangle, square, and pentagon are the subclasses of that. But unless I can mark something as final, which means nobody can inherit from it, everybody can inherit from it. And that can lead to problems if people start using your classes and you make changes to them and they don't know about it. So what they introduced in JDK 15 was the idea of sealed classes. Now what you can do is you can add a modifier to your class declaration, and you can say public sealed class, and you can say that it permits a set of subclasses, and that lists out all the classes that can actually inherit from that, triangle, square, and pentagon. If somebody else came along and said, oh, I like that shape class, I want to create a circle, what's going to happen is the compiler will say, no, you can't do that because it's not in the permits clause, so you're not allowed to extend the sealed class shape. Great. So now we have more control over our class hierarchy. Just a little bit more about sealed classes and inheritance. All the subclasses must provide the inheritance capabilities explicitly. There are 3 ways of doing that. So the first is you can have a sealed class which permits further subclasses. So you can continue to have it sealed with a list of permitted subclasses. You can make it final. So you can say that the square is final, so nobody can then extend that further. And then you can have this sort of slightly strange thing, which is you can unseal it. So you can now use a hyphenated keyword, which is non-sealed. And then you can say, okay, your class pentagon now can be inherited by anybody else. What's interesting is that that non-sealed keyword is a contextual keyword, meaning that it only applies as, or only works as a keyword if it's in that particular place. And there's some very good reason for that, because I could have the idea of 2 ints, which are called non and sealed, and then I could say sealed equals non-sealed, which in this case actually means that I'm subtracting the value of sealed from non and then assigning it to sealed. Right, on to pattern matching. First thing we can talk about is pattern matching with instance of. Now, we're all familiar with instance of operator. Again, Java is an object-oriented programming language. One of the key things in object-oriented languages is polymorphism. We can view an object as any of the types which it actually is. So that means the concrete type that it is, any of the superclasses of that type up to object, any of the interfaces that it implements, and any of the interfaces that its supertypes implement. If we want to determine if an object is of a specific type, we use instance of. And we end up with something like this, where we say if obj instance of string, then we want to do something with it as a string. The problem is that in order to use obj as a string, we have to do this assignment here. So we have to create a new variable of type string, and then we have to do an explicit cast of obj to string and assign it to this new variable. And that's really kind of like unnecessary, isn't it? Because if we've already determined that obj is of type string, surely we could just simply use obj as a string within the true branch of that if statement. And there are solid arguments for why that should be the way that it works, but they decided they're not going to do it that way. So what they introduced was the idea of pattern matching for instance of. And in this case, what we do is we say if obj instance of string. And remember that when I described pattern earlier, we had the pattern predicate. So the pattern predicate in this case is obj instance of string. It evaluates to true or false, so we can determine is it something of type string. If it is, we have a pattern variable now, s. So we say if obj instance of string s. And that way we've got a variable that we can use in the true branch of our if statement, which is of type string. So we're still not treating obj as a string. We have to do that sort of pattern variable, and that becomes the thing that we actually use. So now we can print out the length of the string. Clearly in the else branch, because we don't have something which we've got as a string, then the scope of s is not valid, so we can't use s and call methods on it there. Now we can extend that, and we can say if obj instance of string s, so we've got our pattern predicate and our pattern variable, and then we can add a conditional to that and say and s.length is greater than 0. We know this will work because we know the way the AND operator works is that we always evaluate the left-hand side first, and only if that evaluates to true do we evaluate the right-hand side. If the left-hand side evaluates to true, then we know we have a string, so the scope of s is valid. We can call the length method on it and test against greater than 0. If we tried to do that with the OR operator, that wouldn't work, because again, we always evaluate the left-hand side, but if that evaluates to false, then we evaluate the right-hand side. So if it evaluated to false, we don't have a string, so the scope of s wouldn't be valid. When it comes to the scope of the variable that we have, you need to be a little bit careful because we can invert the test. So we could say if not O instance of string s, return. So if we don't have a string, we return from the method. And that means that the variable s, our pattern variable, is valid for the rest of that method. So you don't have to just think about it being inside an if block. It can actually be outside of that as well. Which actually brings us to the idea of the way that scoping works for pattern variables. And we have what's called flow scoping. If you look at a local variable in Java, the scoping of that variable is from wherever it's declared to the end of the block in which it's declared. So it could be a block of code, it could be a for loop, it could be an if statement, whatever block of code you've got. The other thing about local variables is that they're subject to definite assignment. You can't just leave a local variable without something assigned to it. There isn't a default value like there is for an instance field. So in the case of a local variable, you have to make sure that you assign something to it so it has a value. Pattern variables or binding variables are also subject to definite assignment. They have to have something assigned to them. But the scope of those variables is essentially all the places where they actually have something assigned to them. And that's what we call flow scoping. If we look at the if statement, the place where you have a definite value is the true branch of the if statement. The false branch, you don't have an assigned value, therefore the scoping is not valid. What this allows us to do is to reuse variable names more than we could do with local variables. So now we can do something like if O instance of integer num, and then do something with that. And then we can do else if O instance of float and reuse num. We don't have to have a different variable name at this point. Similarly, we can do if instance of long, we can reuse num. Couldn't do that with local variables because the scoping doesn't work that way. But in the case of our pattern variables, because we can use flow scoping, the places where they have definite assignment is only in the true branch of that if statement, so we can reuse the name. Right, time for a puzzle. I have a piece of code here. Object s equals new object. And then I say if s instance of string, so we're using our pattern predicate, s instance of string, and then we're going to use a pattern variable, also called s. And then we're going to say length of string, or string of length, plus the length, and else no string. So I'm going to give you three options for what happens here. Option 1, the code will work. Option 2, the code will not compile. And option 3, the code will not compile, but it will work. Aha. So, a show of hands. Who thinks the code will work? Aha. A couple of people. Okay. Who thinks the code will not compile? Aha. Good. The majority of people are going from option 2 and option 3. Who thinks the code will not compile, but it will work? Oh, okay, we've got a couple of people there who clearly are looking at the fact that, I've added that, it must be true. Well, let's have a look. So if we put this into a file and we compile it, try to compile it, this is what will happen. So it will say, error on line 5, variable s is already defined in method main. So yeah, we can't reuse the variable name. We've got s as our pattern variable, we've got s as the variable that we're using for instance of. So clearly it won't compile. So you would think, okay, that's the answer, except it's not, because it will work if you use JShell. If you use JSON, and I've literally just cut and pasted from terminal, and I tried this with JDK 23. I've been trying it since, I think, like JDK 15 or something like that. If you do this and you create a new object of type of s, and then you do if s is instance of string s and all the code we had before, it'll print out no string. I have absolutely no idea why that works. And what's even more interesting is that I've shown this to several engineers at Oracle who work on Java, and they have no idea why it works either. They look at it, they go, it's a bug. They take pictures of it. They go back, and it doesn't get fixed. So, right, next thing is pattern matching for switch. So we talked about switch pattern or switch expressions, and we talked about switch statements. How can we use pattern matching here? If we look at switch the way that it was designed initially, and even over time, we're quite limited on what we can actually have in terms of the types that we can switch on. So we can switch on integral values, we can switch on strings, and we can switch on enumerations. What they've done now is to expand that so that you can use type patterns and switch on a type. And we can end up with a piece of code like this. So we say, okay, I've got a method called type tester, takes something of object, and then I want to see what particular type it is and do something accordingly. Now, the first thing that I can do is I can also have a specific case for null. So I can put the case for null and say, okay, we've got a null type there. That's nice because then I don't have to have an external test where I test for null with an if statement. I can include it into my switch statement there. Then I can have case string s. So in this case, our predicate is just string, case string, and we've got a pattern variable called s. And now we can print out the value of s. We can also have a color, C. Now, in the initial build of this, or the initial development of this, we can't switch on primitives. We can now, and I'll talk about that later on. But in this particular situation, when they introduced this, you couldn't switch on primitive. However, an array of primitives is an object reference, so it has a type, so you can switch on an array of ints and then print out the length of the array. And then you have a default. Now, a little bit more about null, because null is special. And in this case, we have null can be used in switch statements and expressions. But if you don't include it, the compiler will put that in there for you. So it's the idea of backwards compatibility. What they want is the code to behave in the same way. If you don't put a specific case in there for null, the compiler will insert it and it will throw a null pointer exception. If we change our code so we don't have an explicit case for null, we've just got our types in the default, and then what the compiler will effectively compile is having a case null, which throws a new null pointer exception. So as I say, it does exactly the same thing as it did before, doesn't break backwards compatibility. You can also combine, because remember, we can use comma separated lists now. You can do case null, comma default. And that way you can handle both the situation where you've got a null or something which is not covered by the cases previously and handle that in the same way. And that, again, makes life a little bit easier for you when you're figuring out what to do with that. Completeness. So this is very important. This is where we come back to what I said earlier on about the idea of switch expressions and needing to be complete. So we have to handle all possible values. If I had something like this, where I've got my type tester, but now I'm just going to have a case for string and a case for integer. What happens if I pass a float or a color or any other type that isn't string or integer? Well, you could argue that because there isn't a case for that in there, you simply treat it as like a multiple if then else type of construct, and you say, well, because there's nothing there, we'll just move past it and ignore that case, that switch statement. But the developers said, that's going to lead to too many possible errors. So what they said was that you have to deal with every possible thing that could be passed to that switch expression or statement. And in this case, what's going to happen is that you need to add something which will handle everything else. And that's easy because what we do is just add a default. So now we've got a default. Any other type that isn't a string or an integer will be handled. Doesn't mean you have to have a default in every switch expression where you're dealing with types, because remember, we can have sealed classes. If we take the shape that I described earlier, where we have a shape, triangle, square, and pentagon, that is a sealed class, a type hierarchy that only has 4 possibilities in it. We can create a switch expression which says, or a switch statement which says, okay, switch on shape, case triangle, case square, case pentagon, case shape. Every possible thing that we can pass as a shape has an explicit case. We don't need a default in that particular situation. So it is complete in terms of what it's dealing with. You can also have what are called guarded patterns. And this kind of goes back to the situation I explained with the instance of pattern, where you can add an and with a test on the pattern variable. Prior to JDK 19, they did the same thing. They used the double ampersand, they used the and operator that we're all familiar with. Then in JDK 19, they decided to change their mind. And they said, rather than using and, which is, well, everybody knows it, we'll use when, because it makes it more readable, I guess. So you get case triangle t when t.area is greater than 25. So we can do a test and we can say it's a big triangle, and then we have a case for triangle on its own, where if we don't pass the guarded part of the pattern, then we'll say it's a small triangle. And then we've got our square, pentagon, and shape. So effectively, it just has primary pattern, which is the thing we're matching against, and then when and a conditional and expression. This only works for patterns. It doesn't work if you're just using a case like case foo, when, something else. But yeah, that wouldn't really make a lot of sense. Right, second puzzle. Confusingly guarded patterns. Right, let's say we have a new sealed class, which we're going to call interrogator. And that's going to have some subclasses which are who, what, where, when, and why. Then we're going to have a final class called when, which extends interrogator. And that's going to have a method in it called when, which returns a Boolean. What we can then do is we can be a bit silly with our code. So we can say, okay, let's have some methods here where, when, and where, why, and when. And then we can have a method called test question, which has an interrogator question that's passed in. And then we have a switch on question, and we can have a case for what, which has a pattern variable called what, and we'll print out what. Same for where, same for why. And we'll have a default, which couldn't possibly happen because, well, we're going to have a sealed type, but we'll have how. And then we can add case who, what, where, why. And we can do that because, remember, what we're doing here is we're saying who is the type of our pattern, what is the pattern variable of our pattern, when is actually being used as a conditional contextual keyword, which is saying that we have a guarded pattern, and then where is the method that we're going to call to determine whether it's true or false, and then why is the method that we're going to call if it is true, and we have a who. So who can guess what the next line is going to be? Case when. And we can actually do this, and the compiler will quite happily compile it. I tried it, I got it to work. So in this case, what's happening is we've got explain what when means, where, and why. Okay, so this when actually is the pattern predicate type. So obviously we're matching against a type of when. Then we've got when as a variable name for the pattern variable name. Okay. Then we've got a when, which is the guarded, it indicates we've got a guarded pattern. Then we've got a when, which is the pattern variable that we're using from the pattern predicate on the left-hand side of the guarded pattern. And then we're calling the when, which is the method on that, to evaluate whether we've got true or false for the guard. And then we call the local when method in order to evaluate, to see what's actually going on. I don't recommend that. It's not good coding practice, but you can do it. Right, puzzle number 3. Right, declaring variable names. So this is where, again, the idea with the way that the switch statement used to work had some issues with like local variables. So if we do something like this, where we've got case 0, 1 on a number, then we can, because we can, I will explain more about primitives later on. We can do case 0, 1, string the equals binary, log that message, and then break. And then we have default where we have not binary, log that message, and then break. So in this case, variable D is already going to be declared because we can't reuse the local variable in 2 separate cases. And that's one of the limitations that we get. So we can solve that by adding some braces around that. So we make it a separate block of code so each of the local variables is in a separate block. But if we use flow scoping, we can have something like this, where we can say string D, switch S, and then we can have case triangle shape, square shape, pentagon shape, and then we can print out all of the variables and things like that. So will this code compile? Yes or no? Who thinks yes? Okay, who thinks no? Okay, one person at the back, right. Well, yes, it will, because the flow scoping allows us to reuse the variable that we had before. So even though we've got D, we can reuse D because it's a local variable externally, and we can reuse shape because it's flow scoping. Puzzle 4. Right, so we're going to use our sealed class again, and we're going to have sealed class shape permits triangle, square, pentagon. Right, so what's wrong with this switch? So now I've changed the order of things, and I've said case shape, print out is shape, triangle, print out triangle, square, print out square, pentagon, print out pentagon. Anybody know what's wrong with that? Very good. Excellent. Yes. So the problem that we have there is that triangle, square, and pentagon are all shapes. So they're all subclasses of shape. So if you use polymorphism, you can view a triangle as a shape because it's the superclass. So that means that what we've got here is code that won't compile because the compiler will say that the case label is dominated by a preceding label. So this is pattern dominance that we can see. Okay. So shape will always match first, so the code becomes unreachable. Very good. What about this? So we can have triangle T, where we've got system print line big triangle, and then we have the guarded pattern afterwards. Well, again, we're going to see the same thing because in this case, triangle will always match any triangle, and we'll never get to the point where we also do the guarded test. So the compiler is clever enough to, question.
Would that compile or not at all?
That won't compile. Yeah, yeah. So the compiler will figure out that that's unreachable. Okay, so the unguarded case is dominating the guarded case. What about this? Okay, so now we're going to put our guard above the triangle, and we'll say case triangle T when area less than 100, print out it's a small triangle. Have a second guard where it's less than 25, we'll print out a tiny triangle, and then we'll have a triangle, square, and pentagon, and shape. Okay, so who thinks this is going to work? You think it'll work? And okay, so in this case, it will work because the compiler doesn't care about the guards. it only cares about type dominance. So it will see the fact that you have a guard above the unguarded type and will say, okay, that's fine. But you can't put the guard below the unguarded one because that would, yeah. No, because what will happen is when you hit the first case, it'll say, is it a triangle? Yes. Is the area of that triangle less than 100? Yes. It'll print out a small triangle, and then it will drop down to the end of the case because it will have matched something. Yeah, yeah. Because if you reverse those two lines, then you actually could it could evaluate it twice. Yes. Yeah, we can even remove the unguarded one. So we can now have just triangle when t.area is less than 100, triangle when t.area is less than 25, because, remember, we've got a shape, haven't we? Yeah, so yeah, what happens when we call shape tester with new triangle 200, which is bigger than any of the guarded ones, we'll actually get shape because we actually match against the shape on its own. We don't match because we failed the two guards. Right, record patterns. Right, so we talked about records earlier on. What we can do with a record is we can obviously match against a record as a type because it's just a special form of class. So if we have our point again that has double x, double y, we can do something like this where we calculate Pythagoras and pass in an object. And we say if it's of type point, instance of point, give it a pattern variable p, and then in order to calculate the length of the hypotenuse, we need to find x and y, so we can extract that calling p.x and p.y. So that's all good, that will work, no problem with that. Good start, but we can do better. So what we can use is record patterns, which are introduced in JDK 19. And record patterns are a form of deconstruction pattern, so we're matching against something, but then we're actually going to extract the variables as well. Deconstruction patterns only work with records, so you can't use it with normal class. So how does that work? So what we can do is we can do this. We can say same code, but this time we say if O instance of, and then we give the full record declaration. So point, double x, double y. By doing that, we're then exposing the x and the y values as pattern variables that we can use in the true branch when we've matched against that pattern. And so we now can call x times x, y times y, without having to dereference through the pattern variable that we had before. So that allows us to do code in a slightly better way. Yeah, pattern variables with record patterns are not allowed. So this was something that they did allow initially, but then they decided that it could introduce situations with ambiguity. So what do I mean by that? So you could do this. You can do if O instance of point P. So you're saying point is the type and P is the pattern variable. So we know that works. What you can't do with a record pattern is this. So you can't say if O instance of point, give the record declaration where you've got X and Y extracted, and then also have a pattern variable associated with that record called P, which if you wanted to do something else using that, that won't work. The reason is because if you call your record, if you use that particular situation and you used a pattern variable which was when, and then you start using a guard on that pattern variable, it gets completely confusing. And there's a point where you end up with a situation where the code that you've written can be interpreted two different ways. And the compiler just says, I don't know what to do. So they said, can't do that. You can't have a pattern variable with a record pattern. Patterns are also composable. Right, what do I mean by that? Well, let's, again, add some sort of code. So we'll have an interface called rectangle. We will have our records point, which we've used before. We'll introduce a numeration for color, red, blue, and green. And then we're going to have a couple of new records which contain records within them. So we've got a color point, which has a point and a color. And then we've got a color rectangle, which has a color point top left and a color point bottom right. And just to make life easier for myself, we'll also implement rectangle. What we can then do is we can say print the color of that rectangle. And we can say if our instance of, and we can use the record declaration. So we can do deconstruction, have color rectangle, color point top left, color point bottom right, and then we can print out top left.c. So fine, that will work. But as I said, the patterns are composable, which means that we can say, right, since top left is a record, let's deconstruct that and have our instance of color rectangle, color point, point P, color C, color point BR. Now, that's another thing to be aware of is you don't have to use the same names of the variables as were in the initial record declaration. You can use completely different names and the compiler will be quite happy with that. So I've shortened that by just calling it BR rather than bottom right. And then we can print out C. But of course, we know that point P is also a record. So we can go one step further and we can have print top left X and say if our instance of color rectangle, color point, point double X double Y, color C, color point BR, print out X. So at this point, you start thinking to yourself, this is not getting more readable, it's getting less readable. So what can we do about that? Well, there's a couple of things that we can do. First is we can use local variable type inference, introduced in JDK 10, the idea of the var keyword. So we can say, in our instance of color rectangle, color point, and then rather than specifying all the types of these things, we just use var and we let the compiler figure out what these things are for us. So long as there's no ambiguity in terms of us having multiple records called point, which have different things that we're storing in them, then the compiler can work it all out and it simplifies our code a little bit. But there's an even better way of doing this, which is to use unnamed pattern variables. I mentioned this as the type that we had earlier on. And this is where we get into the situation where we match against something, but we don't care what it is. And I said there's a good, useful situation for that. What we do now is we use the underscore character. Now, it used to be that you could use underscore as a variable name. Don't do it, but you could have used underscore as a variable name. But in JDK 9, they made underscore, a single underscore, reserved word. If you're really determined to use underscore as a variable name, you can still use 2 or more underscores as variable name. But in this case, what we're going to do is simply use the underscore to indicate that there's something there, but we don't care what it is. So we do this, and we say if our instance of color rectangle, only thing we actually want from that is X. So we say color point, point, var X. That's what we actually want to reference as a deconstruction. But then for the other things, we know there has to be something there so that we can tell the compiler so it can recognize the signature of the record and then fill in the details. But we don't actually want to use those. So we simplify the code by adding the underscore to make it clear, hopefully clearer, what we're actually doing with the variables there. So got no interest in those, let's ignore them. You can also use unnamed pattern variables in a switch. So if you're using a switch expression or a switch statement where you've got types, then if you're not using the pattern variable on the right-hand side of the arrow operator, you can just use an underscore to replace the variable that you would have had there initially. Primitive types in patterns. So as I said, initially the idea was you couldn't use primitives because they're not a true type in the Java language. Array of ints is a true type, but an int on its own isn't. So now what we can do is have instance of and switch extended to handle primitives. This allows us to do things like this. We can say byte x equals 128. Now we can say if x instance of byte, x instance of int, we have an int. If x instance of int I, and then we can provide a pattern variable as well. So we can say it has a value of this. We can also, so we can do things like this, where we can have float value equals get value, and then you can be more complicated and you can say, okay, switch on value, and then you can specify a specific constant, 0 float in this case, and return 5 float. You can have float x with a guard, so it's a float, and we'll do when x equals 1, then we'll return 6f plus 1, and if it's case float on its own, so we've dealt with everything else, then we'll return 7f plus x. So you can do all sorts of things like that. There are a set of detailed rules about how this works, about how exhaustiveness works, because in this situation, things start to get a bit complicated. So rather than trying to explain all of that in the time I've got, it's well worth reading the JEP, which goes through all the specific details of that. Right, another puzzle. Right, okay, so we're going to have test obj, and we're going to test on passing an object into it. We'll switch on O, and now we're going to have case integer I, so we're testing against an integer object, the wrapper class. I will print out integer, case byte as a primitive, B, and we'll print out byte, and default will print out something else. So my question is, what will be the result of test object of integer.value of 42? Anybody want to guess what you get there? Somebody shout? Integer, yes, of course, because we're passing an integer object, so it should be blindingly obvious that yes, we will get an integer. Good. Okay. However, what about if we pass in test obj 42? What happens then? So, okay, so who thinks integer? Who thinks byte? And who thinks something else? Okay, right. Well, the answer is integer. The reason for that is because, of course, we have to pass an object to that method. The only way that we can pass an object to that method is with the auto boxing. So we auto box 42, and this is where things are kind of interesting because, of course, 42 would fit into a byte, but we get promotion, automatic promotion in Java. So 42 will fit into an integer, and so that is what it is going to be auto boxed into. So if it fits into an integer, it gets auto boxed in integer. If it fits into a long, it's too big for an integer, it will auto box into a long, but it won't auto box into something smaller. What about if we do byte.value of byte 42? Who thinks integer? Who thinks byte? Okay, who thinks something else? Ooh, interesting, interesting. So the answer is byte. Now, the reason for this is unboxing, because, of course, we pass in the object there. Now, what the compiler will do is it will say, okay, well, we're testing against both an object reference and a primitive, but because we passed in a byte, it's going to unbox it, and that will result in a byte. So if it has to test against a primitive, it's going to use unboxing. So it will test against both the thing that's passed and the unboxed value as well. So this is where things kind of get interesting. Right, and then what about if we pass in something cast as a short, 256? So who thinks integer? Okay, who thinks byte? And who thinks something else? Yes, something else. Because we're doing the explicit cast to a short, at that point, the compiler will go, okay, if you're going to cast it to a short, when I auto box it, I will box it into a short because you've made it a short. So even though that will fit into an integer, you don't get automatic promotion. The compiler is I guess, clever enough to say, you cast it as a short, we'll make it a short, so it matches against something else. Puzzle number 6. Right, going back to our switch versus instance of. So we'll go back to our sealed class, but this time we're going to make shape abstract. So you can't instantiate it, so it's abstract. Right, so if I do shape tester and I say print out shape details, if shape instance of triangle T, print out t.isosceles, if shape instance of square S, print out s.root, and if shape instance of pentagon P, print out p.perimeter. Okay, so that handles the 3 different concrete classes that we have. If I do the same thing, but using a switch, so same code essentially, I've got case triangle T, case square S, case pentagon S. So my question here is, will these deliver the same behavior? So if I pass things in as shapes, will I get the same behavior if I use instance of with 3 different things, or will I get the same behavior if I use switch? So who thinks I'll get the same behavior? Who thinks I get different behavior? Okay, so the answer is you will get almost the same behavior with one exception. There's the clue, with one exception, which is if you pass in a null. Because if you pass in a null, what you get from the first one, and if I go back, of course, you see, because if we pass in a null, what's going to happen is it's going to say shape details, if shape is an instance of triangle T, it's not, so it'll go past. And then if we do null, we actually get a null pointer exception. So you're actually getting a null pointer exception from the switch statement. Puzzle number 7, right? So patterns and generics. So I said that you can make a record generic. So here we've got box of type T, and it's going to store something called contents. So if I do box of type string boxed equals null, and I say switch on boxed case box string s, what will happen? Null pointer exception, yes, because effectively we've got a null case in there, and because we're passing in, we've got a null pointer exception. All good. What about if I make it double boxed? So I have a box of type string, and I say double box is a new box with a null in it. Now what happens if I pass in that double box and I do case box of type string s. So who thinks we get a null pointer exception? Not so many people. Okay, who thinks that we'll actually, it will pass and it will be okay? Okay, a few people. And I'm guessing most people don't know what happens at this point. And the answer is you get a different exception. So you actually get match exception. Yeah. So what happens here is that because the null is actually inside the box of box, the compiler, they actually had to add a new exception to handle this particular case, because you've got the null is inside the reference, and so it means that S is still null, but it won't match against case null that will be inserted by the compiler. So just be aware of that as a sort of like an edge case for these things. Puzzle 8, right? Primitive types in patterns and safe casting. There's what's called exact and unconditionally exact. So basically what we're talking about here is reference types using instance of and primitive type, case primitive type pattern variable. So we've already seen sort of the idea behind this. So if I instance of byte, print out byte. Case byte, print out byte value is. Okay, so that's all the code that we've seen before. We know how that works. What about if we do this? Right, so let's have int x equals 42. If x instance of int, print out int. Who thinks that will work? So we'll get int. Okay, hesitant. Don't think we'll get int. Okay, we definitely get int. Very logical, because we're saying, is it an instance of int? Well, we made it an int, so it matches. So there's no problem with that. What about we say if x instance of byte? So we've got an int, but we're saying, is it an instance of byte? So who thinks we'll see byte? Nobody. Oh, one person in the back. And so I guess most people think won't see that. And it prints byte, because 42 does fit into a byte. So again, these are the edge cases. So as long as it fits into a byte, the compiler will go, well, all right. Although you've got a 42 as you've got it as an int, but if you want to test it against a byte, because it will fit into a byte, we can treat it as a byte. So in this case, it will work. And then what happens if we do this? If we say if x instance of byte, print out byte, else if x instance of int, print out int. So who thinks we'll see byte? Who thinks we'll see int? Well, we see byte, because 42 still fits in a byte. So it will match the first one, because of course it says, yes, 42 will fit in a byte. What about if we do it the other way around? We say if x is an instance of int, print out int, else if x instance of byte, print out byte. Who thinks we'll get int? Ooh, who thinks we get byte? Nobody. Good, right, because it does print int. It matches the first one, doesn't match the best one. So we'll say, okay, well, it definitely matched against int, so we deal with that. Primitives with switch. So basically, let's do this. So we've got x equals 42, switch on x, case byte, print out byte, case int, print out int. What happens? Do we get a byte or do we get an int? Who thinks byte? Okay, who thinks int? Byte, because again, it fits into a byte, so the compiler will just say yes. If it fits into a byte, we'll match that first. What about if we swap them around and we have int and byte? So who thinks we get int? Yes. Oh, no, we don't, because we get dominance. So we're saying that even though, because anything that's an int, or anything that's a byte is also an int. So then, because of the way that the case works, we don't do that. We get pattern dominance, and so it won't compile. Yeah, int dominance byte. What about if we use wrapper classes? So let's say int x equals 42, case integer I, print out integer int, case byte. So who thinks int? Who thinks byte? Okay. Int, because again, we're just unboxing and the same thing happens, or it boxes it to an integer, and so we match against that first. Okay, int x equals 128. Now we're going to do byte or short. So we've got an int, and we're going to match against byte or short. Will this work? Why will it not work? Very good. Doesn't cover all possible types, so it's not complete. So you could have some, you could clearly have an int. So even though 128 would fit into a short, then we don't get that. So completeness still applies for primitives. Even if we make it final, I don't know why that would actually make any difference. Yeah, it still doesn't make it work. Yeah, the compiler can only do so much. Right, quick fire final round. So let's say int is 65,535, which is a round number for us as computer scientists, or an almost round number. True or false? X is an instance of byte. Who thinks yes? False, yes, because it won't fit into a byte. X is an instance of short. Yes? No? Yes. False. 32,767 is the biggest short, so no. Int. Yes. True, because yes, that would definitely fit into an int. Long. Yes, because it still fit into a long. Float. Would it be a float? Yes or no? Who's yes? Who's no? True. Yes, because it will do automatic type conversion. Double should, yeah, true, because it's the same. Yeah. What about Boolean? X instance of Boolean. Incompatible type. So it won't give you false or true, it'll give you incompatible type. Right, just to summarize then, pattern matching is a very powerful set of language constructs. Very useful, lots of things we can do with it that make our life simpler in terms of syntax and so on. Reduces boilerplate code, much more declarative in terms of the style of programming that we can use. There's also some interesting work going on in terms of like better optimizations that can happen below the covers in terms of using pattern matching versus non-pattern matching type things. That's not all fully baked in yet. Lots of features already included. You will see more pattern matching to come. There was one idea about a deconstruction pattern for arrays, where you could deconstruct an array into values, but that hasn't made it in yet. And there are some other ideas as well. A little bit about Azul, since I'm here, might as well do a little bit of a sales pitch. Basically, all we do is Java, but Java runtimes. So we have two products. One is a direct replacement for Oracle Java, so it's a build of OpenJDK. We provide support around it. It's identical to Oracle direct replacement. So if you're looking for a cheaper alternative to Oracle, we can provide that. The other thing which is more interesting, and that's what LMAX uses, is a high-performance version of Java. So we take OpenJDK, we modify it internally. So we have a different garbage collector that we use called C4, which is the continuous concurrent compacting collector, truly pauseless collector, eliminates the problems of GC latency. And then we also have a new JIT compiler that we've included, which replaces the C2 JIT compiler with one that generates more heavily optimized code. So for things like Kafka, for example, if you're running Kafka clusters, we can do 43% more transactions per second just by changing the JVM. And that's because of the more heavily optimized code that we get. We're also doing some interesting stuff around what we call a cloud native compiler. So we decouple the JIT compiler from the JVM. If you're running 2 vCores in a container, you're going to be throttling a lot of your application capabilities whilst the system warms up. By shifting that to a centralized service, not only can we eliminate the problem of having to do the compilation in the 2 vCore container, we can also cache the results. So as you spin up multiple instances of the same service, we don't have to recompile the code every time. We just shift it back to the service straight away. So that's it. So thank you very much.